So the last few days we've been going over how to write chemical reactions, how to balance them, okay, how to, now we're going to be looking at predicting them, which actually isn't all that difficult, okay? The only thing it requires you to do that's different from what we have been doing is recognize a pattern, okay? In order to predict the products of a reaction, all you have to be able to do is identify what kind of reaction is going on, given just the reactants. Okay? So if I have a reaction written up there that just has two elements reacting with each other, what kind of reaction is it? It's a synthesis reaction. What happens in the synthesis reaction? They combine to form a compound. That's predicting the products. Okay? All you have to do is put them together and you're done. Okay? If it's a double replacement reaction, then it'll have two ionic compounds that are reacting with each other. And then a double replacement reaction, all we do is swap the metals, and we've got our two new ionic compounds. So it's really nothing different than what you have been doing, except you don't actually have the products in front of you. You have to figure them out. Okay? But it's not hard. Every reaction is unique. It has a distinct pattern in the reactants and a distinct pattern in the products. So all you have to do is recognize patterns. Okay? Then you have to balance, which you already know how to do. Okay, so we're going to look at balancing equations. We're going to quickly go through that because you already know how to do it, but I didn't give you the notes on it before. Okay, and then we're going to go over the predicting of the products. Okay, so the big thing about balancing equations, guys, is that we have to obey the law of conservation of mass. So we have to understand that the amount of atoms on the reactant side of an equation must be the same as on the product side. That's why we balance. We use coefficients to balance equations. That's the big numbers that we've been writing in front of compounds. Okay, and we need to understand, obviously, that matter cannot be created or destroyed. So just to reiterate, okay, why we put in the coefficients when we balance. So let's say I have this reaction here. Let's say it's okay. What kind of reaction is that? Single replacement. Okay. So if I'm going to balance this, okay, what we've been doing is putting the big numbers in front of everything. So if I'm looking at this right now, I would probably want to put a 2 here, okay, in order to balance my nitrogens. Right? When I do that, what am I saying? Right, there's 2 of those molecules. If I'm looking at this from like the most basic standpoint. It could also mean that I have 2 times as many of this as I had of this compound here, okay? And that could be in terms of just ratios, okay? Things like that. But what I can't do is I can't say, oh, well, I'll just do this, okay? Why can I not do that?
That means it's chemically bonded.
It means it's chemically bonded, but it also changes the compound, does it not? Now this isn't swapped and dropped correctly. It's not what would have actually happened in the reaction. So I can't ever add those numbers to balance. I can put them in, obviously, if I'm needing them for swapping and dropping purposes or because a prefix told me they were needed, but I don't put them into balance. Okay? All I do to balance is change how much of the compound there is, not what compound it is. All right, so when I do that, okay, I would also need to put a 2 here to balance the irons after that, and then obviously a 3 here in front of the calcium, and everything will be balanced, right? So put those coefficients in just to make sure everyone knows that this is how much of the stuff we have. Okay, so mass always has to be conserved, okay, in reactions because matter can't be created or destroyed. Okay, all matter has mass, so the mass of the reactants must equal the mass of the products. Right? So if I have this chemical reaction here, okay, that we just wrote down. Let's say I started with 10 grams of that calcium nitride and 5 grams of iron. Okay, I don't know if that would be the actual amount, but let's just say that's what I had. I would have to have 15 grams of products. And in fact, when you start getting into like university courses and things like that, you're actually graded on your percent yield. Okay? What that means is, you know how they come in and they give you an exactly measured amount of reactants. You have to perform like several reactions and distillation and all this other stuff and recover some final product. And then you have to weigh it. They have to weigh it, and then you get graded on how much of it you actually produced versus how much of it could have been produced in a perfect situation. Right? So you have to be like super careful when you're doing the reactions. Right? You get a 4% yield, didn't fail the lab. I wouldn't know anything about. Okay. All right. So in this reaction here, okay, we have obviously two hydrogens reacting, or two hydrogen molecules reacting with one oxygen molecule to produce 2 molecules of water. Okay, but we have 4 atoms of hydrogen, 2 atoms of oxygen, and the same thing on the product side. Okay, so which one of these? So this is our reactants here. The top picture is our reactants. Which picture down below shows the law of conservation of mass being followed? D. Okay. Now, D, it's confusing to look at D because you see some of these yellow ones off by themselves. Okay. All that means is that in this reaction, there weren't enough yellows, or there weren't enough reds to take care of all the yellows. Okay. So up here we had 2, 4, 6, 8, 10 of the reds. Okay. 2, 4, 6, 8, 10 reds here, and then we had 4, 8. Okay. So 1, 2, 3, 4, 5, 6, 7, 8 yellows. Okay. It's the only one where there's the same number of everything at the end. Right? And this happens oftentimes in a chemical reaction. You almost never get a chemical reaction where when you mix two things, you had exactly the right amount of both for all of it to react and just be perfect. Okay? Most of the time, you have either an excess of one or a shortage of the other. Okay, so law of conservation of mass, that's probably something you should know. Okay, that could certainly be like a multiple choice item on a unit exam. Okay, I put that statement out there and ask you what is this called, and you can say law of conservation of energy, law of conservation of mass, law of conservation of whatever it makes up, some other thing. Okay, something like that. All right, so make sure you know the definition or be able to explain the law of conservation of mass. All right, so when we're balancing chemical equations, like I said, we already know how to do this. Okay, first off, we write the chemical formula for the reactants and the products. We don't have to put the state of matter in anymore. I really should delete that. Okay, try balancing the atom or ion present in the greatest number. That's what we've always said we should start to do. Okay, and then we use coefficients by going back and forth. Okay, in order to get them all, unless it's what kind of reaction? Unless it's combustion, which has its own unique set of rules. All right, so again, just so you have those in your notes somewhere, okay, they're in the notes package. You don't necessarily need to write them down, okay, because you already know how to do it. Okay? But yeah, we just use the coefficients. Okay, we repeat step 2 to balance each of the remaining atoms. Okay, and then obviously in the final step, always double check. Okay, always double check that the last thing you balanced still is balanced. Because I have a lot of people that are going back and forth and like, whoo, sweet, I'm done. And then they forget to double check and they don't see that the last number they wrote offset something. Okay, and then they'll get it wrong because they just didn't go back and double check. Okay, always make sure you go back and double check at the end. All right, questions on that? Still need that? Sorry, I'm going kind of fast. Okay, so for using this one here as an example of a balancing reaction, okay, we would have copper reacting with silver nitrate, produce silver, okay, and copper to nitrate. Okay, and so that's a single replacement reaction. Okay, so the thing that's present in the largest number right now is nitrate. Okay, it's got a 2 beside it, everything else is a 1, so I'm going to balance it first. So I'm going to go back over to this side, and I'm going to put a 2 beside the silver nitrate. Okay, that balances the nitrates, but it gives me 2 silvers. So I'm going to go back over here and put a 2 in front of the silver to make it balance, and then I'm going to double check everything else. I've got 1 copper, 2 silvers, 2 silvers, okay, 2 nitrates, and 2 nitrates. Yes, it's good. Okay, I double checked it. Everybody all right with that? We're already pretty good.
So the 3 of the nitrates doesn't it?
The 3 in the nitrate means there's 3 oxygens there. Okay, unless the nitrate breaks apart, which happens sometimes, but not often. Okay, I just go with how many nitrates there are. polyatomic ion usually sticks together. Right? You will get some reactions when it starts really challenging you, where it breaks up, and then you have to track it piece by piece. Okay, how many oxygens are there on this side? How many are there on the other side? You got to do it element by element. Okay? In this case, because it didn't break up, I can treat nitrate like an element. See? Okay. The way this one's written, it's actually saying balance it element by element, because technically you would do it that way, but there's no sense in doing it that way if you don't have to.
So what would you getting like actions and stuff for like the nitrate breaks up and you have to track?
Yeah, I'll give you a few that'll test it a little bit, because you'll need to be humbled. Right? You just start getting cocky about how good you are, and I'll humble you. Okay. Predicting the products of a chemical reaction. Okay, I'll give you a minute here. Write these 4 down, okay, and then we'll walk through them, okay, in order to kind of get the hang of how this works. Okay, so let's walk through how this works. The first step in predicting the products of a chemical reaction is to write out the reactants. That part's already done, okay? But you could have gotten this in a word form, which would have said like calcium plus oxygen, and you would have had to write Ca plus, and remember that oxygen comes as a 2. Okay, so that, again, those are the things you have to remember. Okay, that's the first step. The second step then is to identify what type of reaction is happening. So in this one, I have an element reacting with an element. The only reaction type that does that is, okay, what happens in a synthesis reaction? They combine to form a compound. What kind of compound is this going to form? An ionic compound. It's a metal and a non-metal. Right? So I'm going to go CaO. Now, I need to check this because it's ionic. I've got to drop and swap. It's still good. Okay? So this is a -2. This is a +2. So yes, CaO is fine for the formula for that. Something I have to check if I'm making the compounds myself. Now I need to go back and balance the whole reaction. Okay, so I've got 2 oxygens over here, so I'm going to need a 2 here, and then I'm going to need a 2 here. And now it's balanced and predicted. Okay. Now, one thing here, guys, just so you know, and I think I told you this the other day, I don't have a lot of tricks. Okay, but if this was a quiz, one of the tricks I would play was I would have written a question like this. Okay? Because I would catch some of you doing that. Okay? And while, I mean, in the end, it's still 1 oxygen and 1 calcium, that's not how we write an ionic compound. Okay? Always metal first, non-metal second. Okay? But it's amazing how many people I catch on a simple trick like that. So always make sure, okay, that you remember how to write the compounds. All right. For number 2, I have a reaction that starts with only 1 reactant. It's a decomposition reaction. Okay. In a decomposition reaction, I'm just going to write the 2 elements by themselves. So there's magnesium and sulfur. What do I need to check for?
Sulfur's 8.
Sulfur's an 8. I need to double check that I haven't produced any elements that require the little numbers. Okay, sulfur is one of our molecular elements, and it comes as an 8. Magnesium is not, so it doesn't need anything. Okay, but I have, if I forget to do that, will I get the balancing right? Nope. Okay, so it's important to remember that. Now I've got to balance the whole reaction. I got 8 sulfurs over there. I think I'll start with that. Okay, put an 8 here and an 8 there, and I'm good. Okay. All right. For number 3, what kind of reaction is that? Okay, so I've got a combustion reaction here. What are always the products of a combustion reaction? Carbon dioxide and water. That's just one you memorize. Okay, you don't have to think on this one. It's always carbon dioxide and water. All right, then I need to balance the whole thing. Do I need the rule of 2? Nope. All right, so I'm going to put a 3 here. I'm going to put a 4 here. Okay, and then 3 times 2 is 6, plus 4 more oxygens is 10. 5 times 2 is 10. Okay. Okay. kind of reaction is number 4? Double replacement. Okay, in a double replacement reaction, what do we do with the metals? We switch them. All right, so that means hydrogen's going to end up with hydroxide. Okay, we need to make ionic compounds here. Very common mistake is to end up with 2 metals together and 2 nonmetals together when people predict the products. Okay, so hydrogen's going to end up with hydroxide, okay, and sodium is going to end up with chlorine. Then I've got to check my drops and swaps. This is a +1, this is a -1, so that's good. +1, -1, that's good. And the equation is already balanced. All right. So double replacement reactions are actually pretty easy to predict, okay, because you just swap the metals. All right, last one, because we didn't have one of these. So I've got lead nitrate, it's reacting with potassium. What kind of reaction is that? Single replacement. Okay. In a single replacement reaction, the element needs to replace the part of the ionic compound that it is like. All right? So potassium is a metal, so it's going to switch out for lead. All right, so lead is going to end up alone, and potassium will end up with nitrate. Okay, now I've got to check for special elements. Okay, like single replacement reactions, you got to check for everything. I got to check for special elements because I'll produce one. Okay, here I didn't. It's not. It just produced a metal, so it doesn't need any numbers. Right? And then I've got to drop and swap my ionic compound. This is a -1. This is a +1. So that one's written the way it's supposed to look. Okay. Now I've got to go back and balance. The nitrate's out of balance, so I need to put a 2 here. And where else? In front of the potassium. Okay. Is that a whole lot more difficult than what we were doing? No. Okay. As long as you understand what those reactions are supposed to look like, it's pretty easy to put in the products. Yes. Okay. All right. So I am going to make a copy of this for everybody. It's just a flow chart. You probably won't even need it. Okay. You won't be able to have it on a test or anything like that, but it's just sometimes people like to have it for the first few days while we're doing it. So I'll photocopy that here in a few minutes for everybody. Okay, it basically just says, here's the steps. Write out the reactants, swap and drop ionic compounds, check for special molecular elements when you're writing out the reactants. Okay, if your reaction has 2 elements, then it's synthesis. Put the elements together into compound. Okay, if you need to swap and drop, then balance the reaction. Okay, if it's 1 compound, it's decomposition. Split the compounds, write the elements separately. Okay, check for special molecular elements and balance. Okay, if it's CnHY plus O2, it's combustion. These are always the products. There's the balancing rules. Okay. If it's an element, an ionic compound, it's single replacement. Okay, look at the lone element, identify if it's metal or non-metal, then use it to replace its counterpart in the ionic compound. Swap and drop your new ionic compound, check for for any special elements, and then balance. So like I said, single replacement is the most to do. Okay, in a double replacement reaction, it would be 2 ionics. Swap the metals, swap and drop your new ionic compounds, and balance. Okay, that's all the stuff we've done already. All right, I want you guys to try those ones there. Sorry, I know I have 2 number 5s now because I made one up. But so you guys go on those. Okay, I'll give you a few minutes to go over. Okay, so looking at number 5, I've got element plus element. So this is a synthesis reaction. All right, so I'm going to get beryllium iodide on this side. Okay, beryllium is a +2. So when I drop and swap, I've got +2 and -1. Okay, so this is going to be BeI2, and it's balanced. Okay, for number 6, I've got potassium reacting with iron 2 oxide. Okay, how do I know it's iron 2? Yeah, just because this is a -2, this has to be a +2. Okay, all right. So it's a single replacement reaction. Potassium's a metal, so it's gonna swap with iron. So iron will end up alone, Okay, and potassium will end up with oxygen. All right, so this is a -2, this is a +1, so I'm going to have K2O. Does it matter if I write the iron second and the K2O first? Makes no difference whatsoever, whatever order you do it in. Okay. All right, now I've got to balance the whole reaction. I've got 2 potassiums there, so a 2 here will fix that. How many people have done 7? Okay, let's go to that one too. All right, so we got CuSO4, okay, so copper 2 sulfate reacting with magnesium chloride. That's a double replacement. So what am I going to do with copper and magnesium? Switch them. Okay, so that means copper ends up with chlorine. Okay, magnesium ends up with sulfate. Okay, this now here's the trick. Copper has more than one possible charge. Do I need to know what it is for the other side? I do. Okay, so I got to figure that out. Sulfate's a -2, and there's one of each, so copper must be +2. All right, that won't change. Okay, just so you know, if you have a multivalent metal with more than one charge, whatever charge it is at the start is the charge it is at the end. I'm not changing its charge in a reaction. Okay, that would mean I was actually changing what kind of copper I had, and in a reaction I can't do that. Okay, so this is still the copper that's 2+. Okay, so this will be CuCl2. This is a +2. This is a -2. So that compound is fine. Okay, now we need to balance the whole reaction. Done. Okay, because it's already balanced. I should really make up some harder ones. How many people have done number 8? Okay, because number 8, you're not really predicting anything. You just have to remember that a combustion reaction produces CO2 and water. Okay, so if we're looking at our balancing, 4 is an even number, so I start with, okay, 2 times 4 is 8, and 8 goes there, 2 times 10 is 20, 10 times 2 is 20, and then I look at my oxygens. I've got 10 oxygens in the water, 16 more here in the carbon dioxide for a total of 26. 13 times 2 is 26. How many people have done 9? Okay. So I've only got a single reactant. What kind of reaction is that? Decomposition. Okay, so I'm going to have rubidium end up by itself, phosphorus end up by itself. What do I have to check for? Molecular elements. Phosphorus is one of them, rubidium is not. Okay, so I can leave rubidium the way it is. But now I need to do some balancing. I've got 4 phosphorus over there, so I need to put 4 of them over here, which gives me 12 rubidium. Okay, how many people have done 10? Okay, let's go over it. So on number 10, what kind of reaction is it? Okay, it's double replacement. So first thing I'm going to do is just write out who goes with who on the other side. Okay, so lead's going to end up with phosphate. Okay, and cobalt is going to end up with chlorine. Okay, cobalt and lead are both multivalent metals. So I need to figure out their charges on the reactant side so that I can drop and swap the compounds they're in on the product side. Everybody with me? Okay, so chlorine is a -1 and there's 4 of them. So there's 4 negative charges. That means this lead has a charge of 4, because lead can be 2 or 4. All right, so I'm going to go over here. This is lead 4+. Phosphate is a -3, right? Yeah. Okay. So I'm going to go 3 and 4. All right, so that one's dropped and swapped correctly now. Cobalt, okay, that also is a multivalent metal, so I've got to look here. Phosphate, we already said, is a -3, so that's 6 negative charges. I need to get 6 positive charges out of 3 cobalts, so cobalt has a charge of 2. Right, so +2, -1, COCl2. All right, so now I need to start looking at my balancing. I could start with phosphate, but I have a feeling like I should start with lead. I don't know why, but I just sometimes have these gut reactions when I look at a reaction. Okay, so I'm going to balance lead first. So I'm going to put 3 here. How many chlorine does that give me? 12. Okay, so I got to go over here and put a 6 in. Okay, that gives me 6 cobalts. If I go here, okay, and put a 2 here, does that make everything work? Yes, it does. Sometimes you got to go with your gut. Probably would have worked if I started with phosphate too, but I just had this guy. And let's actually start with that. Okay, that's about as tricky as it. Because that one had multivalent metals, polyatomic ions. It had to predict, it had to be predicted, all that kind of stuff. Okay. All right, how are we feeling about that? Okay. So we're going to work on that some more on Friday, but for right now, we're going to do the pre-lab stuff.